This video will discuss the definition of an integral in calculus. So let's suppose we have our function f of x, and let's suppose that there's another function capital F of x, such that f of x is the derivative of capital F of x. Okay, so in that case, the relationship between f and capital F is that little f is the derivative and capital F is the integral. So capital F of x is equal to the integral of f of x dx. So, and in principle, there would be a constant back here, but once again, this is not mathematics, this is chemistry and physics, so we're not going to worry about that for the moment. So I'm going to say f of x is this, and this is what we call an indefinite integral. So an integral which does not have definite bounds of integration, as we will see in just a moment. Okay, so we can also have what is called a definite integral, where we have our integral sign here, and then we have our limits of integration, our lower limit a and our upper limit b of f of x dx, which is equal to big F of b minus f of a. And this is called a definite integral. So an indefinite integral goes under unspecified ranges, so it's integrating the whole function, and a definite integral is integrating over specific bounds and evaluating the integral function there at two specific points. Okay, so let's look on our graph here. Let's look at a and look at b. So f of x is like the derivative of big F. So a is some value of x, b is some larger value of x in this case, and the integral from a to b is equal to the signed area under the curve from a to b. So from the f of x to the x-axis, the x-axis is below f of x here, so all this area under here is positive area, which is adding to whatever the value of this definite integral is. And then on the negative side here, f of x is below the x-axis, so it's contributing negative area to the sign here. So this area is going to subtract from this area. So the overall result is, as I mentioned, so the area under the curve, and I'll say area in quotations because, as I mentioned, it's not our traditional notion of unsigned area, it's signed in that some of it can be negative. So the area under the curve from A to B is equal to the integral from A to B of f of x dx. And I messed up here, this should have been little f. Sorry about that. All right, we're going to correct that. Okay, much better. All right, so the definite integral represents the area under the curve between two given points for that curve. All right, so how are we going to get this value, and what are we going to use to define as our limit for what this equals? We used a limit for two different points getting arbitrarily close together to get our tangent slope for our derivative. So we're going to use a similar type of idea here to get our integral. So let's say we have the value xi, and xi is equal to a, our initial value, plus, let's say delta x I, where we say delta x is equal to b minus a over n, and n is some number between 0 and infinity, which is a positive number. So is somewhere between 1 and infinity is the value of n. All right, so we can say that the integral from a to b of f of x dx is equal to, or let's say approximately equal to, the sum from I equals 1 to n of f of xi times delta x. So what does this equate to? So what we're doing is we're breaking up the function into little rectangles. So delta x is this value here, the width of a rectangle, and f of xi is the height of the rectangle. So over the entire range that we've got here, we've broken up the function into little rectangles, and we're adding up the area, either positive or negative, of all those rectangles to get our integral. So you can imagine if these rectangles are very big, this integral will be more approximate because we're making bigger errors in the gaps here. And as these squares get smaller, as we have on the right, this integral gets more accurate because those errors get smaller and smaller as these little squares get smaller and smaller. So that's the limit, which is the difference between doing something finite, like delta x, and doing something infinitesimal, like dx. Remember, dx is a very, very small infinitesimal change of x. So it's the value of f of x times a small change of x over the entire region. So the integral is actually the limit as this delta x gets infinitely small. So we'll define that now as the integral from a to b. And notice that this integral is this kind of, I think that's a German character, which is sort of a sideways looking s. A sum is a sigma, so that's a sum. This is a sum from a to b. So the integral from a to b of f of x dx equals the limit as n goes to infinity. Notice that for the derivative we had a limit as h went to 0. Now we have a limit as n goes to infinity of sum I equals 1 to n of f of x sub I times delta x. So it's the limit as our little squares get infinitely small and the errors go away, and we have the exact area under the curve of this function. So we'll have, just as we did for derivatives, various rules for simple functions, a couple combination rules, but unfortunately we won't be as lucky to get exact rules for all cases, because in many cases the integrals won't be exact and we'll have to resort to various approximations, such as Taylor series, which we just saw.